from Duke University, and he will speak about sharp non-uniqueness for the Navier-Stokes equations. So let me just maybe put everybody, pretty much everybody is muted but me. Okay, wonderful. So please.
Okay, so first of all, thank Hanjut and Camille for the invitation. So today I'll be talking about a recent result on the shock non-uniqueness for the incompressible Navier-Stokes equation. This is joint work with my thesis advisor, Alexei Cheskidov. So the talk will consist of 4 parts. So the first part is about some background on this problem, classical and modern results, and then I'll present the main theorem. After that, I'll talk about a little bit about the proof. So first of all, this is the incompressible equation. We consider this equation on a flat torus, so with the periodic boundary condition and no external force. So in the equation, U is the velocity field and P is the scalar pressure. Because we're on torus, so you can find a elliptic equation to find the unique zero mean pressure for the, associated to the solution, and we mainly talk about weak solution and focus on dimension 2 and above. So here's a little bit about the classical theory. So for any divergence-free initial data, there's always one Leray-Hopf solution in this regularity class, finite energy and finite dissipation. So you can, because we're on torus, you can do this by finite dimensional approximation. And those approximate solution will satisfy this energy equality. But when you use, when you take the weak limit, the weak solution will satisfy the energy inequality. And then you can do this construction in any dimension you want, as long as the initial data has finite energy and it is divergence free. So there's always one Leray-Hopf solution. And the question we are concerning is about regularity and uniqueness and energy balance in dimension 3 and above. Because in 2D, it is well known that Leray-Hopf solutions are unique and globally regular. Because uniqueness is not known in dimension 3 and above, we have some conditional result. So by the Zenska-Podin theorem, if in addition your solution is in such a LP LQ space, so P is in time, Q is in space, then you know that this solution will be unique among all possible Leray-Hopf solutions starting from the same initial data. So one strong solution in the Leray-Hopf class will imply the uniqueness for all the Leray-Hopf solutions starting from the same initial data. And this is often referred to as the weak strong uniqueness in fluid dynamics. And it's very important that we have this energy inequality for Leray-Hopf solution, because this weak strong uniqueness is not true for general weak solution. So the proof use both weak formulation and the energy inequality. And if we look at this LP LQ space, and then we consider the natural scaling of the equation, right? So if U is a solution, then U lambda is also a solution, and then you evaluate this U lambda for this LP LQ norm, and then you discover this 2 over P plus D over Q equal to 1 is the critical scaling for this equation, meaning that under this parabolic scaling, this norm does not change. And this formally suggests that 2 over P plus D over Q should be the uniqueness or non-uniqueness threshold for weak solution, for Leray-Hopf solutions. And then to take a look at the regularity of the Leray-Hopf solution, right? We have L infinity L2 and then L2 H1. You can use Sobolev embedding to find that H1 scales like this LP space 2 over d over d minus 2. So formally, if you put this into the umbrella of this LP-LQ scaling, you discover this this line of scaling for the Leray-Hopf solution. And because the dimension is bigger than or equal to 2, so in 2D, these two scaling coincide. So this in particular confirms the well-known uniqueness and smoothness for Leray-Hopf solutions in 2D. But then when the dimension gets large, in 3 and above, there is a scaling gap between this Leray-Hopf solution and the uniqueness threshold. So this leads to the following conjecture, which is the non-uniqueness for Leray-Hopf solutions. Right? So this conjecture is wide open at the moment, before or after this work, but there are some partial results like numerical evidence, and also some conditional results by Lady Zenska and Jia and Seberg. And all this work suggests that Leray-Hopf solutions are not unique in dimension 3 and above, but we still don't have a rigorous proof. So this is a very difficult question. Instead, we are going to consider a more general class of weak solutions. Right? So for if we look at the weak formulation for the Navier-Stokes, this is the weak formulation for the Navier-Stokes. This phi is the test function. So this weak formulation makes sense as long as your initial data is in LP, and that your vector field is L2 space-time locally integrable. So you don't need the L infinity L2 and L2 H1 of the Leray-Hopf solution to make sense of this weak formulation. And in fact, this weak formulation is not so weak because by this classical result of Phelps-Jones rivalry, we know that a weak solution is in fact in the integral solution. Right? So weak solution also solve the following integral solution. So this P is the Leray projection. So it projects vector field to the onto the divergence-free vector field, and then here this E Laplacian is the heat kernel. So we have this kind of weak strong or weak mild equivalence, and in fact this formulation, this mild integral formulation, also allow us to recover the same uniqueness threshold as the Leray-Hopf solution. So if you potentially have a non-Leray-Hopf solution, right? So just a weak solution solving the equation in this distributional sense, and this solution is in the LP-LQ class with this scaling, then we know that this weak solution is unique. So you cannot have two strong solutions in this class, and in fact, we can show that these kind of solutions are Leray-Hopf. So if you go above this threshold, there is only one kind of solution, which is the Leray-Hopf solution. But then by all those regularity criteria, these solutions are regular for positive time. So above this critical level, all weak solutions are classical solutions. So and this interesting scaling threshold is the same as the Leray-Hopf solution, and is related also to the parabolic scaling of the Navier-Stokes. So from the classical theory, we can ask two questions. So the first question is whether weak solutions in this type of LP-LQ class, but below this regularity threshold, are unique. So here the initial data is understood in the sense of mild formulation. So this may not be attained in the usual LP sense, but sometimes it's in the sense of distribution. So whether there are two different weak solutions such that they have the same initial data. So this is the question one. And the second question is, does there exist weak solution that is not Leray-Hopf? Because so here we are on torus, so it's a compact domain, and sometimes people use the integral equation to construct so-called mild solutions, but because we are on torus, those solutions will have finite energy, and then you can show that in fact those solutions agree with Leray-Hopf solution for a short time. So from the classical theory, it is not clear whether there is a weak solution that is not Leray-Hopf, that violates the energy balance law. And also, if we can somehow manage to show the sharpness of these two conjectures, then you see the non-uniqueness of the Leray-Hopf solution becomes intricate, right? Because above this, because if you are more regular than this threshold, your weak solution become Leray-Hopf. So these are the two main motivation for today's talk. Okay. Now I'm going to talk about some modern non-uniqueness results for the Navier-Stokes equation. So the previous two questions, in fact, have a positive answer due to the work of Bukamasta Leco in 19. They showed that weak solutions are not unique in this CL2 class, and the solution they construct are also non-Leray-Hopf, and then you can plug this into the LP-LQ scaling that we are considering, and then you see they scales like this. So the right-hand side is d/2, which is very far away from the critical scaling of 1. And later, Buckmaster, Colombo, and Becot, they discovered that in the previous scheme, there is some tiny room there that can be used. So you can subtract a tiny positive epsilon on the right-hand side. But again, this is also very far away from 1. And myself also consider this problem. And in fact, in high dimensions, this epsilon will become large. And in 4D in particular, you can take a meaningful constant 1/200. You can take put it on the right hand side, but still this is still very far from the threshold of 1. Okay. So all these constructions are non-Leray-Hopf, and these are all proved by the convex integration technique over this last decade, right? So this technique was also used in solving the famous Onsager conjecture, and there are many people working in this domain. And here is a non-complete list of the contributors to this technique in incompressible fluids. And people also use this technique to in compressible fluids. So this list is by no means complete. So here's the question. So the main question is, can we reduce this number d/2 on the right hand side of scaling? So basically, can we improve the regularity of all these convex integration solutions, and then to show that those classical uniqueness results are sharp? So that's our main motivation. And before I introduce the main theorem, here's some background about partial regularity in time. So for Leray-Hopf solutions in 3D, we know that they are almost everywhere in time regular. meaning that in fact we can find a set which is a union of some open intervals, and then if you look at the solution restricted on those on this union, it is in fact a classical solution. Right? And if you look at the potential singular set, right, you remove this union, and you can have a very good Hausdorff dimension bound on this set, right? So this set is not so large, so it has Hausdorff dimension less than 1/2 in 3D. But as you but this 1/2 the 1/2 is sharp in terms of the scaling L2H1 for the Leray-Hopf, but we don't know if this is sharp in terms of upper bound or lower bound. We only have this upper bound estimate, and at the moment we don't know whether there is a Leray-Hopf solution with a non-trivial singular set in time. And also, if we keep increasing the dimension, in 4D already, we lose this bound. We know that in 4D, Leray-Hopf solutions are still almost everywhere in time regular, but we don't have the bound on the Hausdorff dimension. And in 5D and above, we don't know whether Leray-Hopf solutions are partially regular. So they can be nowhere regular in theory. And again, this theory of partial regularity is only true for Leray-Hopf solutions. This is not the case for general weak solutions. And they can be nowhere regular. If you just take a look at the construction of Bookmaster code, those solutions are nowhere regular. They are only L2 and slightly above L2, but nothing further. And concerning this partial regularity, for Bookmaster Colombo Vicol in the same paper, they construct a class of non-Leray-Hopf solutions with this kind of partial regularity in time, and such that this singular set in time is non-trivial because you have uniqueness. Some bad things happen, so this singular set is not trivial, and you have a nice bound on this singular set in time. So the Hausdorff dimension is strictly less than 1. This again, this epsilon is very tiny, but it is bigger than 0. Okay, so now I can present the short version of our result. So recall the previous 2 questions, right? So in dimension 2 and above, you fix P and Q, satisfying this scaling bigger than 1. So this is in the supercritical regime. And then the first question is whether weak solutions are unique in this class. And the second question is whether there is a non-unique, non-Leray-Hopf solution in this LP-acute class. So that's the 2 conjecture. And with Alexei, we are able to solve this in a at a particular case when Q is infinity. So for all dimension 2 and above, and you take your P as close to 2 as you want, then if you have a weak solution in this class, right? So in particular, you can use a classical smooth solution, right? Because this requires 1 interval of regularity. So you can take a classical solution, and then I can cook up another solution in this class so that these 2 solutions share the same initial data. So this in particular implies the non-uniqueness in this LPI infinity class. And because this construction destroys the energy balance law, in particular, this implies the existence of non-Leray-Hopf weak solution in the same class, so LP infinity. So this is the shorter version, and clearly we are able to solve this only at the endpoint Q is equal to infinity, and the rest of the cases are open. So So this is so the short version follows from this the main result, right? So the setup is the same. So you take your dimension, you take your P and Q and a positive epsilon, and you give me a divergence-free smooth zero mean vector field, and then I can cook up a weak solution of the Navier-Stokes, and with this solution, I can find a set, which is a union of open intervals, such that the solution is in this LP on infinity and L1W1Q class, and my weak solution does not deviate from the given vector field too much, so it's bounded from above by epsilon. And then my solution restricted to this union of open intervals is a classical solution, as the case for the Leray-Hopf solution. And this solution also agrees with the smooth solution emerging from the initial data of V. And we have a very good bound on this singular set in time. So the Hausdorff dimension of the singular set in time can be as small as you want. Okay. So this is the main theorem, and then I'll be presenting some comments relating to this result. So here is a graph to compare different current so to compare different non-uniqueness results. So the horizontal axis is the time scaling index 1 over Q, and then the vertical axis is the spatial scaling 1 over P, right? So previous non-uniqueness result of Buchmaster-Vicot and Buchmaster-Colombo-Vicot are on this vertical axis, and because and then they are very close to this L infinity L2 class, and so here, and the critical class is L infinity LD. So here's I take the continuity because for this class of uniqueness result we need continuity in time, but they scales the same nevertheless. Okay. And if we also look at the scaling for the Leray-Hopf solution, right? So it scales from L2, L infinity L2 all the way to L2H1, which is the same scaling as this LP LQ space. And depending on the dimension, this could be higher or lower than this CLD, depending on the dimension. And I draw this blue line because the solution will satisfy the scaling on this whole line, but not for this results. So these results will only satisfy the scaling at this exact points. You can move them up and down a little bit, but you don't have a whole line of LP LQ scaling. Okay, and our new result is right here. So it lands just at the horizontal axis of time scaling. So L2 L infinity is critical for all dimension because the criticality line is 2 over P plus D over Q is equal to 1. So we are able to show non-uniqueness right here. And previously, it's only known on this vertical axis, and it's very far away from this critical scaling. And now we can do this on this horizontal axis all the way to the critical threshold. And because our solution has intervals of regularity, if we look at some higher Sobolev norm, say HD, which is supercritical, then the solution may look like this, right? And on each intervals of regularity, this quantity is finite, but near the left point, the norm may blow up. But this is only one possibility. The solutions may stay bounded in this HD topology as t goes to the left point. It is unknown, and there's no way you can go across because this structure is totally disconnected. Okay. So here is the common. So here are some comments for the main result. So this is the first 2D non-uniqueness result, right? So in 2D, weak solutions solving the Navier-Stokes in the distributional sense are not unique. Right? And you may notice the 2D Navier-Stokes is L infinity L2 critical. So if you just apply the framework of Buckmaster-Vaco, it does not work, because their theorem says uniqueness in CL2, which contradicts this criticality of 2D Navier-Stokes. And our method is L2 space-time critical, so it works beyond the usual critical threshold. So for the regular Navier-Stokes, we can do this in 2D, or you can put higher power of the Laplacian term. You can increase the strength of the dissipation. This method will also work, but of course there's an upper limit, but that upper limit is different than the usual critical threshold referred in the literature. And our bound on the singular set significantly improved the previous bound, right, which is only 1 minus epsilon, and we can do all the way to epsilon. And the last.
Sorry, can I interrupt you a second? Can you comment on this fact? So you're saying you can do hyperdissipative in 2D too?
Yes. I can do hyperdissipative in 2D as well.
So what is actually the alpha at which you would stop then? What does it depend on?
Yeah, it's you find the space where this L2 space-time is critical.
Okay.
So for regular Laplacian, it is L infinity L2 critical. So if you keep increasing alpha until you find this is critical.
Okay, until that. Oh, okay. Okay. I was confused. So, but the L infinity L2, of course, you will not be able to do. I mean, you have to give up on the time summability, I guess, right?
Yes.
Yeah. Okay. Now I'm fine. So, but if you keep L infinity L2, then the Laplacian is critical.
Right. So you have to
and then alpha would be actually equal to 1. Okay.
Yes. Right. And
okay.
Yeah. And the last point is actually a little bit controversial. We didn't prove this in the paper, but in theory, if you use more bookkeeping, you can achieve non-uniqueness in L infinity based in time space as well. So this is what's known as the largest critical space for the Navier-Stokes. So any scaling invariant critical space will embedded in this space, right? So if you are slightly away from this space, say you put more negative derivative here, or you slightly decrease the spatial interchangeability, then we can also show that our solution lives in these two spaces, right? But what's more important is this method will only work if you estimate the solution in L infinity based space in space. Right? So in space it has to be L infinity, or you have the most negative derivative in space. So this does not work if you use say h1 half in 3D, right? So this we cannot do. So this is very difficult, but we can do something scales pretty much the same, but it is L infinity based. But this we can do. So the very same theorem holds for the Euler equation, right? Incompressible Euler as well. So we do not use any parabolic regularization. So all the good properties that I stated also hold for the Euler equation as well. And now we can do interpolation. So LP L infinity and L1W1Q will give us anomalous dissipation in this L3, almost L3 halves in time, and exactly held 1/3 in space. And we can also do L1C1 minus because of this Q can be arbitrarily close to infinity. So we can get arbitrarily close to C1 in space. And this anomalous dissipation is very interesting because all the previous construction for Euler, for incompressible Euler concerning the on-cycle conjecture, those solutions live strictly below this C1/3 in space. So the best possible is C1/3 minus epsilon or minus a log, but you cannot do exactly C1/3 if you insist continuity in time. But here we are not continuous in time. Here we are only L3 halves in time, and this allows us to get exactly C1/3 in space. So if you look at the best possible current energy conservation criterion, it says L3 in time should be the right scale if you insist on this C1/3 in space. So if you and clearly this exponent 3/2 is not optimal. The optimal one should be L3, but it's not too far off either. And finally, if you are familiar with Euler, you will see this L1W1Q scales the same as the Biot-Mitre criterion for for unique continuation. Right? But these two are different kinds of results, right? So Biot-Mitre is for continuation of a strong solution, but here we are not considering any strong solution. Right? But my point is these two scales the same. And in this inviscid case, because we don't have the dissipation, the kinetic energy is piecewise constant on those intervals of regularity. Right? So the energy is piecewise constant in time, but somehow there is anomalous energy influx or energy dissipation on those small temporal scales. Okay. So now I'm going to talk about some main idea of the construction. Again, this is built upon previous work on convex integration. And here we use a two-steps approach. So we consider this Navier-Stokes Reynolds system. So here Rn denotes the symmetric traceless matrix called the Reynolds stress, and this measures the difference to a exact solution of the Navier-Stokes. So we're going to construct a sequence of approximate solutions Un Rn such that each Rn is supported on a union of many small intervals that occupies a very small area. And then we will going to show that this solution Un will converge to some limit in L2 spacetime LP L infinity and L1W1Q topology, so that the solution U is a weak solution, because you need this L2 spacetime regularity to make sense of the weak formulation, and the latter two are our regularity requirement in the theorem. And of course, the stress should decay, the error should decay to 0 in some topology. And here we use the weakest possible topology, which is L1 in space and time. Okay, so the first step is to concentrate the stress error. So you give me Un Rn, I will somehow concentrate the stress error so that it is supported on a union of smaller intervals. And this this step does not change the error or the solution too much. It changed the solution a little bit, but but not too much. And the error stays pretty much the same. And I'll specify the meaning of that later. So because we are not decrease the error, we have to use another step, which is convex integration. And here we use a new variant that kind of reduce this error in space time. So the first step goes like this. So you give me un rn, and then I'll split out un bar and rn bar, so that un is very close to un bar, but rn bar is supported on smaller intervals than rn. And then the union of my new smaller intervals can be fitted into that of the previous one, right? So the union for Rn, right? So the second step, so according to this notation, is from un bar Rn bar to un plus one and Rn plus one. So this is where we reduce the size of the stress, right? So after this step, the error, so this R is very close to 1. So this error will decay in this L1 LR topology. And the perturbation, the size of the perturbation in L1 space-time relates to L1 L1 in space-time of this Rm bar. So if you can see that these two will imply the theorem. So now we do the first step, which is concentrating the stress error. So we drop all the subscripts for convenience, right? So basically, all we do is to solve the Navier-Stokes exactly on each tiny interval. So if you look at the equation for this VI, it is designed so that U plus VI is an exact solution on this interval. Right? And this tau is a free parameter at our disposal. I'll take this as small as I want so that there's no blow up, so that the solution is unique and smooth, because everything here is smooth and I start with 0 initial data. Okay? So in particular, this U plus VI will be smooth on the interior of each interval. And because already the given data are, it's supported on a small set in time, many VIs will be 0. Now we have pieces of exact solutions, right? So U plus VI solves the Navier-Stokes on each interval. So I'll just take a cutoff. Right? So I'll just take a cutoff. So this is chi I. It's 1 most of the time, but it decays very sharply near these two ends, so Ti and Ti plus 1. Right? So the length is tau to the epsilon, and epsilon is very small, and the cutoff scale is tau. So this cutoff is very sharp compared to the length of the interval. And after some computation, you can find this is the new stress error, right? The first and the third term are fine because this chi is mostly 1. But the second one is a problem because when you have time derivative hits chi I, it's going to be huge, right? Because your cutoff is very sharp. But nevertheless, it turns out you can obtain such estimates, because you can think about this because it is L1 in time, it cancels exactly this one derivative on chi I, and we can only do for p bigger than 1 or less than infinity. It's because some technical reason of Calderon-Sigma a singular operator, but this is not very essential. And what's more important is this implicit constant is independent of the timescale tau. Okay. So that's more important. So in other words, if you do this, then you successfully concentrate all the stress error, and it only costs you a constant multiple in time when you do this when you do your estimate in L1 in time. And then we have to look at the size of the correction, right? So we are adding this to the existing solution. But because each vi starts from 0, and then tau is tau epsilon is the length scale for each interval, right? It grows linearly at most. So because tau is a free parameter, we can decrease tau as small as you want, so that by continuity each vi is very small. But this estimate is only at the level of L infinity in time, right? As I said, when you have time derivative, this estimate will be huge. Okay, so after this step, I find a new pair of concentrated solution, U bar and R bar. R bar supported on very small intervals, and it is a exact solution of the Navier-Stokes most of the time. And I have a little bit larger than we start with, but not too much. So we need a additional step of convex integration to reduce the size. So that's our new goal. Our new goal is to find a convex integration scheme that is compatible with error decaying only in L1 in time topology. Right? So here I'll recall previous convex integration scheme for the Navier-Stokes. Right? Usually you start with this ansatz. Right? You take a linear combination of suitable building block. Right? So the amplitude depends on the previous error, and then WQ are suitable divergence-free vector fields. And you plug this ansatz into the equation, you find this divergence equation for this R1. And if you can do this by exploiting the cancellation in here, then R1 should be much smaller than you start with. And if you so here is just some computation to confirm this ansatz, right? So the previous approach goes like this: you look at this leading order interaction, which is the this high to low interaction here, and then after cancel the previous error, you have this term, which is a high frequency in space, and then some pressure gradient, which is harmless because we don't impose estimates on the pressure. So this high to low cascade in space will balance the old stress error, but this is incompatible with our goal, with our step 1, because this cancellation is pointwise in time, and pointwise in time our concentrated stress error is huge. So we need something that's L1 in time. So the new ansatz is to use the high to low cascade in space time, so that the O stress is only canceled weakly in space time. So instead of pointwise in time, we are doing this weakly in space time. So we consider this type of ansatz, right? So if you look at the nonlinear term, somehow you manage to use all the cancellation, and then you have one group of terms which is of high spatial frequency, and then you have another group of terms which is of high temporal frequency, and then some pressure gradient, and that's the main idea for this space-time scheme. So to implement this space-time scheme, we take some function in time. There's a ton of freedom here. You can choose any bump function you want, right? So in time, and you have like just this type of small bump function satisfying this type of estimate. This is very easy. You just rescale the bump function and then periodize this so that it is on 0 to t, right? So 0 to t. And then you just multiply this factor to the existing perturbation, and for specifically in this paper we use the stationary Mikado flow, but in fact you can use pretty much any say Beltrami flows if you insist. This is not very important. And then because of this introduction of this kappa and nu, you have 4 parameters, right? So you have spatial oscillation, which is here, and then spatial concentration, which relates to the support set of our spatial building block WK, and then the new addition of temporal oscillation and concentration, right? So for oscillations, we do convex integration, right? Convex integration in space and convex integration in time. And for concentrations, we use those to treat interchangeability for regularity. So just an example of how this estimate will go, right? So if you look at L2 in space time of this W, because this has L2 in times critical scaling. So essentially you just follow the previous approach, you should get this estimate. So as long as we have decay of Rn in L1 space time, then we will have the convergence of Un in L2 space time. So the question becomes, how do we get the decay of Rn in L1 spacetime? So if we look at the equation for this new stress error R1, and then this solves this divergence equation, most of the terms can be handled by the previous approach, right? So if you, in particular, if you look at the estimates for the linear term, right? It's pretty much just the gradient of the perturbation in L1 spacetime topology, and this is encompassed by this L1W1Q estimates of W. So I'll just ignore this and focus on the main part. The main part is the oscillation part, and then the temporal derivative part. Because we introduced temporal scaling, right? Temporal oscillation and concentration. When you have derivative hitting a temporal derivative hitting the perturbation, it is going to be a problem. So we have to keep track of these two. These two parts are the most difficult parts. And if you record this heuristic, right? So high spatial frequency plus high temporal frequency. And in fact, you notice that this term is exactly equal to this, because the introduction of this intermittent factor G kappa, and because G kappa, right, we record this has a square mean of 1, right? So this factor has very high temporal frequency, because G kappa oscillates as frequency has a period of mu minus 1 in time, right? So this is this term oscillates much faster than this R. That's why I call this high temporal frequency term. And because there's no there's only divergence of R in the approximate equation, so I cannot put this into part of the new stress. I have to cancel this. Right. So this is also inspired by the Bookmaster Vico 19. We can just integrate in time and introduce a new character. Right. The purpose of this character is that the time derivative of this balance exactly this this error. I believe I messed up some sign here, but nevertheless, just the role of this character is to balance this term of high temporal frequency and plus some harmless error, because this error carries a factor of mu minus 1, and you see all this derivative are hitting R, and R is fixed, so you can take mu to be as large as you want, so that the second term become as small as you want. So this is not a problem. And then the first term cancels this difficult term in the computation. So and also so this error is fine. And if you look at this corrector, this guy also has a mu-1 in front, and all the derivative is hitting the given data. So we can increase this nu as much as we want, so that this this WO is as small as we want. Right? So for instance, in infinity H100D, right? we can do this, because you take any derivative, all the derivative are hitting this R, because there's no spatial frequency term. So all the derivative will be hitting R. So we are fine. And now we are going to I'm going to talk about how to choose the 4 parameters so that we can get to the desired LP L infinity and L1 W1Q regularity. Right? So we start with this baseline regularity. So L2 in space-time, right? It is bounded by this L1 space-time of the previous error, right? So this is the previous error. So you have a little bit of decay, because the previous error decays like 2 to the minus n. So you have a little bit of decay. This is our baseline regularity. And so to get to LP L infinity, just increase in space and decrease in time, right? So you trade in temporal interchangeability in exchange for spatial interchangeability, right? So you I think there's a minus sign, right? I think this is not the one. So it should be kappa 1/2 minus 1 over p and mu to the d minus 1 over 2, right? So this guy is huge, but this guy has a negative exponent. So so it is fine. So it is possible to accommodate this, right? So this is negative, right? This is negative. And if you look at this L1 W1Q, right? So you can so you go from L2 in time to L1 in time, so you gain something. But then you go from L2 in space to W1Q in space, so you have one derivative and some concentration term, right? So here it is. And also there's another constraint, which as I mentioned is this temporal derivative term, right? And then this constitute this type of estimate, and then so basically you need to balance all these 3 constraints at the same time. So the idea is but in the end it is possible to balance all these 3. The room is very small, but it is possible. And so I'll just right. So my point is it is possible. Okay. So now we come to the final conclusion, right? So we have a sequence, right? It converges to one vector field in this topology, and Rn, the error, goes to 0 in L1 space and time, right? If you collect all the bad set, which are the supports for this Rn, then you can define this interval of regularity as this union of the complement of all the bad sets. And because these bad sets Bn are decreasing, right? So it's equal to lim sup, and by standard covering lemma, this lim sup can be bounded by the dimension can be bounded by epsilon, because by definition it's this tau m minus epsilon many interval of size tau n. So by covering lemma, this is the Hausdorff dimension is less than epsilon. And we finished the construction. And thank you for your attention.
Thank you. Can you make the dimension 0?
I don't know, but in the estimate, the constant depends on epsilon, so that might be a problem.
So, but you have to balance the. So it's not really like you choose the parameters one after the other. I mean, is there like. So what I didn't understand is in all these balances, can you really choose like, for instance, nu completely up to you, or I mean, like you just have to choose it bigger, or it has to satisfy still some constraints?
Yeah. So pretty much all we take. So there are 4 parameters. All 4 parameters are some power of a major frequency parameter. So you are just choosing the power of that, right? And you just reduce everything, and you have a set of constraints. And luckily, there is a solution.
But you don't have a window, so like you couldn't take, for instance, the sort of largest parameter and make it an exponential. It has still to be a power.
I think so. And the second step is independent from the first step. So if you don't want in any interval of regularity, you can forget about the first step. You just iterate using the second proposition, just do convex integration. Then you have a nowhere smooth solution satisfying the same type of estimates.
Is there any way you could push it to p equal 2?
P equal to 2 is critical. So if you go P equal to 2, then you have to decrease Q, right?
Yeah. No. Okay, sorry. Absolutely. No, what I meant was, but maybe this I got wrong from your statement. So you fix a p less than 2 and then you construct a solution, right?
Yes.
So can you make actually one which is in all of them? I mean, that is what I meant by pushing p to 2 somehow, like making it in the intersection of all the spaces.
I'm not particularly familiar with this type of result, but judging by previous results, it seems possible. Because there are previous type of results by Sakatahiti and Mandana, they have this type of intersection of all the good ones below the threshold, and all I can see is that it just kind of. My point is I don't see why this is impossible, but maybe I'm just naive.
Well, so somehow to me it seemed closer to the I mean, somewhat similar to the question that I asked with the dimension, right? Because of course the dimension of that set is 0 if you can just show that for all the, I mean, it's very similar. So you fix a p, you fix an epsilon, and then you find something which works. If you could find something which works on all the scales, you would you would get like every p less than 2, and then you would get, of course, that it's dimension less than epsilon for every epsilon, which is the definition of having Hausdorff dimension equal to 0.
That's worth looking at. Yes. Yeah, I haven't thought about this. Right.
Okay.
What's more difficult is.
Other questions? Yeah, you were saying?
Yeah, I was saying what's more difficult is to cover the rest of the regime, because current results are on this vertical line, and here we are on the horizontal line, but everything here is unknown.
Well, I guess you're taking all the, I mean, you're like putting all the bad part on time, sort of, right?
Yes.
And the other construction is putting all the bad part on space, somewhat. It's doing an infinity in time.
Yeah.
So it's unclear how you would actually mix the two strategies to kind of, you know, balance a little bit between the two.
Can I ask one technical question? So you are working on 2D also, and you use the Mikado flows. Then how do you deal with the intersection parts?
So there are two ways to deal this problem. So first of all, we have the freedom to choose the intermittent factor, right? You can, for each flow, you can assign a factor that's disjoint from others. So the Mikado flow will be disjoint in space-time. That's one way. That's the easiest way, but not in the paper. In the paper, we just look at the intersection, because in 2D, the pipe flow has a very thin radius. So the intersection will have one more degree of smallness, because the length is 1 and the thickness is mu minus 1. If you have intersection, there's 2 mu minus 1. That implies the smallness.
And that's enough to control the problematic part. Okay, thank you.
Okay, if there are no other questions, thank you.